Hello, I'm George, N3VQW. This month's presentation is on antenna analyzers. Due to the coronavirus, we are not able to meet up for the April club meeting in person, so we are using an online format. I've decided to record my presentation in a video format so that people can watch it online. What is an antenna analyzer? It is a device used for measuring the input impedance of antenna systems. An antenna analyzer is a common tool used for troubleshooting antennas and feed lines, as well as fine-tuning their performance. Standing wave ratio. How much of the power provided to the antenna is reflected to the source? So how much power you're getting back from the antenna to the radio. If the SWR is too high, it could definitely damage your radio. Typically, you want to have as close to a 1-to-1 ratio as possible, no more than 2-to-1, 3-to-1. A lot of the inexpensive built-in antenna tuners cannot handle more than 3-to-1 SWR on your radio. Impedance, the effective resistance of an electric circuit or component to alternating current, arising from the combined effects of ohmic resistance and reactance. Resistance, the degree to which a substance or device opposes the passage of an electric circuit, causing energy dissipation. Ohm's law resistance, measured in ohms, is equal to the voltage divided by the current. Reactance is a form of opposition that electrical components exhibit to the passage of alternating current because of capacitance or inductance. Resistance and reactance combine to form impedance. So as you see, all these measurements interact with each other. Example antenna analyzer, the MFJ269C. This particular model has a variable oscillator, a frequency counter, a frequency multiplier, a 50 ohm RF bridge, a 12-bit A to D analog to digital converter, and a microcontroller. All those allow this to perform a wide variety of useful and RF impedance measurements, including coax cable loss and electrical distance to an open or short in the coax. This could be used in measuring antennas, testing tuners, testing all kinds of RF related equipment. So it's a pretty versatile piece of equipment. The antenna analyzer has a display which shows you the frequency and other measurements. And of course, the dials show the SWR and ohms, which would be the impedance. The main tune knob is what you use to tune the frequency, and these little knobs here change the frequency range. It's pretty simple to operate, it really is. So this is the MFJ269C. This is a manual analog antenna analyzer, and I have this plugged into my Hustler 5B TV, which is in the backyard. And this top number here is the frequency that it's set to, and as you see, is greater than 31 SWR. And this right here is the impedance of about 15 ohms at that frequency. So what we want to do is go to this frequency that we want to measure. So let's set this to 7.200 megahertz. So we're in lower range. So we don't want the lower range, do we? Yes, we do. So we want to make sure this is set to 4.7 to 11. This is set to lower range, and as you can see, we now set to a frequency of 4.563 megahertz. So what we're going to do is we're going to turn this knob until it says 7.2 megahertz. So I'm turning the tune knob, and a little bit goes a long way. So as you see, the impedance changes, and the SWR needle is changing too. So you could do the sweep manually here if you want to. So I'm at 7.1, and as you can see, the SWR is now 1.5 to 1.5, and the ohms is closer to 50. So I'm going to get closer to 7.2, and like I said, a little bit goes a long way here. 7201. Okay, close enough. So at that frequency, not only do you get some entertaining radio on that frequency, but it's this SWR is 1.4, and it's at 56 ohms there. I think it's at 60 there on the gauge, but yeah, SWR. You can also do a little sweep here manually, like if I wanted to see what the lower range of this thing is. Well, definitely the antenna doesn't resonate very well on. So 7.0, it's 2.0, and at 7.3. It is 1.5. Another type of antenna analyzer is the digital analyzer, and this particular model is an MFJ226. It's also known as a vector network analyzer. And the definition of vector network analyzer is contains both a source used to generate a known stimulus signal and a set of receivers used to determine changes to the stimulus caused by the devices under test. That's a Wikipedia definition if I know one. But basically, it means it has a computer in it that does a bunch of digital checks on it and gives you information. So, it's really fancy. In other words, it's a digital analyzer. And these digital analyzers are useful because you can do automatically a single frequency, or you can do a sweep of frequencies. In this particular examples here, we have a single frequency that's being measured, and then it shows the impedance, SWR, reactance, and resistance measurements on the screen in these examples. It can measure the impedance of series and parallel, and there's a couple of examples here where it's doing measurements, a little schematic showing how the analyzer would be wiring that test. In sweep mode, you can enter start and end frequency for the measurements, and a graphical chart is drawn for the different measurement types. And in this example, you can see that the frequency of 7.25 3 megahertz, the SWR is 1.44 on the sample antenna, impedance is 38.7, resistance 37.5, reactance 37.5, and of course it also measures the return losses in dB and degrees and the phase angles, and it also draws a Smith chart. This is the digital analyzer, my MFJ226, and it has several different modes here. The first one is single frequency, and that basically is single frequency. And as you can see, I have 7.2 enter here. And to enter that, you just type in whatever frequency you want, 7.20, okay, and it'll measure it. So I can go like 14.3, okay, 28.3, okay. Let's do something ridiculous that this antenna does not support. 18.1, okay. Yeah, it doesn't do that, 17 meters. Okay, so that's single frequency. But this will also show other measurements. That will show the SWR. Let me go back to a frequency here that this will measure. Okay, 7.2. So if I go to the next screen, the SWR is 1.449, and then the Z is 62.3 ohms, R is 59.1 ohms, and X is 19.7. And do you remember what those measurements are? Z is the impedance, R is the resistance, and X is the reactance. So Z is the impedance. So keep that in mind. It doesn't say, it's not very friendly, it doesn't say impedance, whatever, but anyways, that's what that is. So on the next screen, shows the impedance in series. And if you remember your amateur radio exam, you would measure impedance by adding them together. For example, resistors. You know, you got two 100 ohm resistors. If you add them together in series, you have 200 ohms. So, and this is in parallel. And if you remember the formula for the parallel, you're doing the reciprocal calculation. Yeah, that's a lot of fun. So, yeah. And then, of course, we have the rectangular and polar measurements here. And that's it. Okay, let's do the sweep. It gives us an option of what we want to measure. So I'm going to say SWR. And it's going to do a chart. And I have the start frequency set to 3.6. I have stop frequency 29. And scale set to 10. It shows everything on the chart here at 10. And we don't need to calibrate. We don't need to load any calibration data. And we don't need to save the file. Oh, by the way, save the files. You can save your measurements to memory. And then you can download it into some software on your computer and show the charts, the graphical charts on the computer. Or you could actually control this directly from the computer. We can move the little cursor, see the line going across, that's the cursor. And what you do is you move the cursor to the lowest point, and that will be the lowest SWR on the frequency. So you can see here saying that the SWR is at 1.46 at 7.22 megahertz. And you can see on these frequencies like 9, it doesn't resonate very well. SWR is really crazy there. And then next is 14 megahertz, so 20 meters. And then the next low is 21 megahertz, which is SWR of 1.7. And then on 10 meters, it will be low 2. There is a low over here on the 80 meter band all the way to the left here, but it's not showing on the chart. There we go. 2.16, 3.8 megahertz. The antenna is resonating on, but it's, as you can see, there isn't much of a gap there. You go off of that, it doesn't work well. So measure the impedance. It'll do the same thing. It'll just draw a chart. And then you can see what your impedance is at different frequencies. So 15.4, 48. So 4.4 is at 48. You can measure reactance, return loss, phase angle, and then of course we have a Smith chart here. Another type of analyzer on the market is the NANO-VNA. And this is not particularly an antenna analyzer, but it measures the same components that you would be measuring on an antenna: SWR, impedance, reactance. But the advantage of this device is that it costs a fraction of an antenna analyzer. Both the MFJ 226 and this MFJ 269C are made for amateur radio. They also have a hefty price tag. I looked at similar models. These range between around $300 to $500. And this digital analyzer, this is the MFJ one, so it's at the low end, is around $300. There's other analyzers made by other brands that cost more than that. So these are amateur radio specific, and this is not amateur radio specific, but this is $50. So there are some trade-offs. These are much more finely tuned, but these things will work in a pinch. This is the NANO-VNA, and this isn't exactly an antenna analyzer, but it can be used as one. On the top here you have a USB charging port, and also that port will allow you to read information controlled by the computer. We have the power switch, and we have the control knob here that also acts as a button. And as you can see, this is not exactly encased in a case, so it really would be inadvisable to operate this outside, especially in a wet environment. And also, you don't want to be touching the unit while you're making measurements because that tends to affect the results. So I'm going to turn this thing on. Alright, so before we get started, we want to enter the frequency range that we want to measure. So this is a touchscreen. So I'm going to enter a stimulus, start, and I'm going to say 3.6 megahertz. I'm going to say stop, 29 megahertz. And notice I am using a pen because the touchscreen is actually quite difficult to work with your fingers. Because this is kind of like high resolution and it's hard to press the right button with your fingers. So, now we need to calibrate it. Every time you do a different frequency range you haven't done before, you have to calibrate the unit. Now you can save the calibration so you don't have to do that later, but we're going through the whole calibration process. And this does come with the calibration tools. You have the test components here. So this is the 50K resistor, and we have an open test and a short test. So here's the procedure for calibrating. So I'm going to go back to the main menu, calibrate. And what I'm going to do is I'm going to go to calibrate, and I'm going to say this is going to be the open calibration. So we can use the open connector if we want to. So I'm going to put that on channel 0. And say open. Okay, that's done. Next on the list is short. So I'm going to connect the short. We'll hit short. Now we got to do load. So we're going to connect the 50K resistor to the load. Go ahead and say load. And then this is isolation, so nothing connected, isolation. And then through. So we're just going to connect both of the channels together with one of the wires. So we'll do that. And say through, then done. And then we can save this as slot 0. So next time I can load the calibration from slot 0. Okay, now we have this unit calibrated. We can go ahead and plug my 5B TV in and see what it says. I'm going to plug this in. And right now it's showing the impedance. That's the green line on the Smith chart. And but I want to change the yellow line to show SWR. So to do that, I'm going to say, go back to the main menu, display, trace. I'm going to make sure trace 0 selected. By the way, trace 0 and trace 2 are both on channel 0 is trace 0 and trace 2, and channel 1 is trace 1 and trace 3. So if you plug anything in here, only trace 2 and trace 1 and 3 can be measured off of that channel, and 0 and 2 could be measured off this channel. So I'm going to make sure trace 0 is selected. Let's go ahead and hide these other traces here because, make it a little less confusing. So trace 1, and I'm going to say format SWR, and now that's going to show the SWR. As you can see, I have a chart here that's very similar to the chart that was produced by the MFJ digital analyzer. So as you can see, if I go to this low point here, SWR is 1.3, and the frequency is around 27.4 megahertz. At this low point here will be 15 meters, 21.3, and SWR 1.45. 18 meters is similar to what it was on the other one. Yeah, 18 point something. SWR of 2.71 actually can be correct. SWR on 14.014 is 1.19. At next low peak is at 7.156 according to this, is at 1.39. So it's not exactly the same numbers that you got on the actually tuned amateur radio analyzers, but it's close enough. And then of course we got this dip here on 3.6 at 2.62 megahertz. So it's a little off, but this is just the basic nutshell of how to operate this little NANO-VNA. And of course you get more information on YouTube about all the other measurements you can do. Let's go back to turn trace 2 back on, and that will be the impedance. So what this little arrow here tells you what it is. So at this, the impedance is 19.6. It's quite high down here. Down here, it's at 61. And then 43. And 49, so close to 50 there. Earlier I had mentioned that you can actually control the MFJ226 and other analyzers using software. The MFJ226 is actually a rebranded Times Technology analyzer, and this is the saved results I did earlier this month on the 5B TV, and it's pretty cool. So around 21.606 megahertz, 13.7 megahertz there, 14 megahertz, I guess is low SWR. This is the measurements I got when I measured the SWR on the Comet antenna I have in the attic that I use for my packet station. And as you can see, the minimum SWR is around 100 to 1, so there definitely was a problem. And it turns out it was a connector that plugs into the radio on the feed lines. After I fixed the connector on the feed line, this is how the antenna measured. And let's see if we can find the frequencies. 145.0 megahertz. I'll just say 0 megahertz. 1 megahertz. Okay, that's close enough. The SWR is 1.18. That's what it should be. Instead of being 100 to 1. Yeah, so this is a much more realistic and more acceptable measurement. So as you can see, the antenna analyzer, and as you can see, the antenna analyzer definitely helped me see that there was an issue with my packet station and what the problem was. And that concludes this presentation. Again, I'm sorry I was not able to present this in person due to the circumstances of the coronavirus outbreak, but I still, thought it was important that I put this presentation together so that there would be a topic for this month. Anyways, this is N3VQW 73s. See you next month.